So let's start. So this is the last lecture of chapter 8, yeah? So we'll go over a few questions or example problems that you can expect next week. Okay, so the exam 2 next week counts for 20% like exam 1, exam 3, and the quizzes count for 5%, as you know. And so the questions, the example problems that we discussed today in class, those you can expect next week. And not the same question, of course, but very similar. Okay, so again I highlight that study those scripts because it might be a little difficult without. Okay, and again, you can see me do this stuff, and you think, oh, I can do this, I don't need to study. But trust me, on the exam, one thing is a little different and you're stuck. You don't know what to do anymore. Whereas if you practice, then you do know what to do. Okay, one other remark is that this class, 15% of your grade is the lab attendance, and you can miss up to 2 lab lectures, okay? The TAs, they keep track of who's there and who's not there. That's one. So that's 15% of your grade, and the exams are 20% of your grade, so 3 times 20 is 60, so 60 and 15 is 75. Then the quizzes are 15% total, each 5%, 3 times 5 is 15, 75 and 15 is 90. So we have 10% left, and 10% is the final project, okay? You will do a final project based on a certain problem that is handed to you. The class will be divided in about like, about 38 groups or so of 5 students, okay? And I assign those students. In the past, the first time, I let the students decide which group they want to be in. And even after 4 weeks, that wasn't decided. I had one student who was in 5 groups. Okay? I got really annoyed after a while because I had to figure out everything at the end. Yeah? So that's why, unfortunately, I tried to be nice as always. And I was at the end of the line, I was, it took a lot of my time. So now I just assign the groups. Can I make small changes under some circumstances? Yes, it has happened that under certain conditions, 2 people cannot be in the same group for some reason. And it could be a good reason, like, yeah, this person is chasing me or whatever, stalking me. There's all kind of reasons that could be a reason. Some of this has happened in the past, okay, believe it or not. Okay, so today, again, we will summarize chapter 8. So I will hand out those groups, by the way. I'll do that next week, okay? And then we'll also go over the problem itself. We will go over that in the coming 4 weeks where I'll give more and more information. But I suggest that you start early, preferably like in next week is week 6, I believe. No later than early week 7 or so, that you start talking to each other in the group, yeah? Because you have to turn in a final code that I will check, and you'll have to turn in a report, okay? And what needs to be in there, that's all going to be made very clear. And based on those results and the code, we will be checking the codes with the TAs. We will checking all the codes, then we'll compare them against each other, and that will decide who's going to get an A, who's going to get an A+. Typically, the grades are A and B, okay? We try to be helpful, okay? There are some groups, if you don't turn in anything, you're going to have an F for that part, okay? It's 10%. But you have to do a really bad job, generally, to get a C or lower, okay? So try to get an A, because that means that already 25% of your grade is an A. And it means that we can ask more difficult questions on the exam, yeah? Okay, so what we'll start with today, we'll go over the material in chapter 8 and a little bit the material in chapter 7, okay? Just what you can expect next week on the exam. So, we'll talk about 3 different problems. The first one is a simple test function, and we're trying to find the root of that function. That's essentially finding the root of a function is similar to solving a system of equations. Because if you're solving a system of equations, you're essentially trying to find the coefficients of that system for which the left-hand side is equal to the right-hand side. Now that's very similar to finding the root, because essentially you're trying to find that point for which the function value itself is 0. So in other words, you could reformulate that in a linear system of equations or nonlinear, where the right-hand side minus the left-hand side is equal to 0. So f0, that function, that built-in function, has a lot of things in common with Gaussian elimination. So we'll illustrate that here. So can we always start with clear and close all, yeah? So I clear this whole thing, my memory, clear all, and then close all, and then I'll call to the top of the screen, yeah? Now, example 1. Very simple, you will laugh, you will run away, but we'll just reiterate. Let's consider the following function. Y is x squared minus 4. Now, we would like to find the roots of this function. So it was a question today in the quiz, yeah? What is the root of a function? I told you this in class, and now there's the recorded, so you just write them all down. But unfortunately, not all the students had it correct, as I predicted. It always happens. But now, we would like to find the roots of this function. Now, how do we do that? How do we find the roots of this function? Now, I told you, if you're really lost, then the first thing you do is you just plot that function, yeah? That's what we did here. We just add some labels and we define the actual horizontal, the y-axis here. You see that that's in black. So what we see here, we're trying to find the roots of this function. The function is y is x squared minus 4. That's in the nice, very nice red line. And then the black horizontal line is y is 0. And now what is the definition of the root? The root is that location, that value of x, for which fx is 0. Now, a function x squared minus 4, we know that the root must be minus 2, because minus 2 squared minus 4 is 0. Minus 2 squared is 4. 4 minus 4 is 0. Another root of this function is 2. Because 2 squared minus 4 is 4 minus 4 is 0. So this function has 2 roots. We all know this. Now the question is, okay, we know this analytically, yeah? So, but how can the computer come up with this answer? We can see this graphically, but we like the computer to tell us what the root is. Now, we can use this f0 built-in function that gives us the root of a given function with a certain argument x in this case. So I have defined my function here as an inline function, yeah? So x squared minus 4, and again I use the dot here so that I can work this, that this function works with a vector or a matrix if so desired. If I don't have the dot here, it's not going to work with a vector. That's only going to work with x that are scalar values. So for each different scalar, you need to rerun the function. We've talked about that, but just to reiterate. Now, so how do I find the root? What we see here, oh God, we have 2 roots. So f0 should be giving us 2 different answers. Now, how do we do that is we just start f0 at 2 different locations, okay? So we start f0 at minus 5. So if we start at minus 5, we start over here. And likely f0 is going to move in this direction. And then at this point it's going to say, hey, I found the root. Because when it moves further, it notices the function becomes negative. So here you have the sign change. So in bracketing, it would give an interval around here. Okay? Now, so what is R1? Oh, minus 2. So if we start at minus 5, the root is minus 2. Now, but we want to find both roots, so if we want to find the other root, we start at 5. If we start over here, what you'll see, it moves in this direction, and it should find, and I should have called that R2, that R2 is 2. So I have 2 roots. And so how can you find all the roots of your function with f0? Is you just start at different locations. Different starting values. I use 5 here as starting value for the second root. That's why it's called R2. That's not the R2 statistic, okay? So don't get confused. Oh, that's for later, I believe. So R1, this is R1, and R2 is this one. So this is R1, this is the first root, and this is the second root. And you just change, you can plot the function, that's my suggestion. So if you're lost on the exam, there's some complicated function, and we ask how many roots does this equation does this function have? The least you could do is plot that function, and you can just see, like how many roots you just calculate. You might not be able to get it perfectly, but you can start zooming in, zooming in, zooming in. That's not the desired solution, but at least you have an answer to the question, okay? And you should be able to plot any function by just specifying an inline function. Yeah, you specify that function in here as the inline function. And once you have that function, then you can plot it. Yeah, we know how to do that by now. Now, so this was easy. This is the use of F0. Okay, and we'll get back to F0 in a little bit. Now, second example. Now it gets a little harder. I like to know that value of x for which line 52, the left-hand side is equal to the right-hand side. For the value of a is 3. So that's line 52. Yeah? So I have this equation here. This is the equation I have. And I know that a is 3. So I have an x at both sides of this equation. But you'll agree with me that it's really hard to find an analytical solution that will give you the solution of x for which both sides are equal. I can move 1 over the square root of x to the other side. I say it's equal to 0 then. But then you have to find x. How do we do this? Now, this is where the residual comes in. Because now we have an equation at the left-hand side. We have an equation at the right-hand side. And ideally, we have x is something. But we don't have that in this case. So what can we do is, the first thing that we do, we actually plot both sides of this equation. We plot the left-hand side and we plot the right-hand side. And we try to find that value of x for which the left-hand side is equal to the right-hand side. Yeah? Now, we just plot both sides of this equation. So we define x is between 0.1 and 10. And I don't specify how many value of x, so it's 100 automatically. I say a is 3, so a in this equation is 3. So I define that here. Then I open a second figure by saying figure 2, open that one, because I don't want to override this figure. Yeah. Now I plot the left-hand side here. This is the left-hand side. And then I define labels. I have an x value, y value, yeah? And now I plot the right-hand side. Here. So what I end up with is something like this, where I plot the left-hand side is in red, the right-hand side is in blue, and now I try to find that value of x for which both sides of this equation are equal to each other. So what value of x should this be about? Where are we? Which value should that be? Where do these two functions cross each other? Yeah, around that value are both sides of the equation, 1 over the square root of x, which is the blue line, and the other one, the red line, the right-hand side, they're equal to each other. But unfortunately, how do we do this in practice? We like to use F0. But now we have an equation on the left-hand side and we have an equation on the right-hand side. So how do we do this? Now, what we do is relatively simple, and this is where the residual comes back in. Is what we do is we actually move over the left-hand side to the right-hand side. Okay, so now we have the following inline function, where this was originally the right-hand side, and this is now minus the left-hand side. And that's our new equation. And now we're trying to find that value of x for which this difference is 0, because when these two functions cross each other, you see that their difference in y value is 0. So you're trying to find that x value for which the difference of the two y values is 0. Now that's what we did here. We specify a inline function here. That's essentially the right-hand side minus the left-hand side. You can also do it the other way around if you want to. The left-hand side minus the right-hand side. It doesn't matter. Just move one part of the equation over to the other side and set it equal to 0. This inline function needs to be equal to 0. Now, that's what F0 was developed for. Yeah, so now I start F0 with my inline function. This is called the residual because it's the difference between two things. Remember, residual in the context of the nonlinear or linear system of equation was model minus data, left-hand side minus right-hand side. Now, it's the same here. It's the left-hand side minus the right-hand, or right-hand side minus left-hand side, or the other way around. It doesn't really matter. Just the minus or plus doesn't really matter. So R is now our root is f0, the function is this one, and my starting value is 1. So what is the r value here? You see it's 1.1546. Now if I do, what's the function value at this r value? This should be 0. And you see it's really small. It's almost 0. And this EPS value, this really small value in Matlab, which you can consider this as a numerical error. I cannot calculate more precise than this value. You see that the value of the root that we have is smaller than this epsilon value. So in other words, it's really highly accurate. You could say that this is 0. Okay? All calculators make errors. And why is in chapter 5 of the book. But we didn't go over that because one quick thing, Matlab doesn't calculate with these numbers that we see there. Matlab works in the binary space, like all computer languages. They work in the binary space. So, because they work in the binary space, they represent all the numbers in the binary space. And some numbers you cannot represent in the binary space, because you only have so many bytes. Sometimes you hear like 256, 64, etc. You've heard that maybe. And because of that, you're limited in what you can represent. And that introduces rounding errors. So, and there's some nice examples in chapter 5, but we're not going to talk about it because chapter 5 is very confusing for someone that just starts to know how to just start practicing computer programming. It's useful once you really start to really understand the material. But that's why we skipped it, because it's confusing. And it's not necessary, it really breaks up the book. So, anyway. So R, 1.1546. And does that make sense? Now, we can use the zoom in here, yeah? So we'll start zooming in. Here, up. Imagine that we got a different answer here. Oh, God. Reset, we'll start over again. Oh, we have time left. I think it's accurate enough here, yeah? What is it? 1.15. There's a small difference, you see that? And why would this be? It has to do with the plotting. Like, we only have 100 values between 0.1 and 10, yeah? Which are pretty accurate, yeah? X values, remember? We plot this function between 0.1 and 10. And we use 100 values. And these are nonlinear functions, as you see. So when the interval, when it gets, the intervals are then like, what is it, 0.1? Yeah, 0.1 to 100. And that in 100 steps. That's an interval of about 0.1, a little smaller, because you start at 0.1, not at 0. So 0.1 to 100, but anyway. So we have intervals on x of 0.1, so we have intervals on y that have an x interval of 0.1, and that's why this falls really within that interval. So that's why these functions that we see here, they're interpolated between two successive x values. And so it might not be perfectly, what we get here might not be perfectly aligning with that, but you get a pretty good value, yeah, over here. It's almost perfect. So anyway. So here, this is the root value here, with the same thing that we got. Now, so far, this is important. So this residual thing you can expect next week. So I'm going to give you a different equation, but the same principle. Okay? Now, you can also expect something like example 3. So imagine that we have collected some data of x versus y. Imagine, for instance, that I collected the relationship where x is the temperature and y is the associated air pressure. So I went to the airport, whatever. They always have very nice measurement stations over there with wind speed, wind direction. I measured the temperature there and the air pressure. And that's what I have two data values. I have x and y. X is temperature, y is air pressure. And this is just a relationship, okay? And this is just hypothetical, okay? So I have two data sets, or I have one data set here with different pairs, okay? With x and y. So if x is 0, y is 2. X is 2, y is minus 30, etc. Air pressure doesn't become negative unless you specify it from a certain reference value. But anyway, I have these values here. Now what I like to do is I like to fit a function through this data. And the function that I want to fit through this data is y is an unknown coefficient x1 times x to the power 3 plus c2 times x squared plus c3 times x plus c4. So this function has 4 unknowns. Yeah, c1, c2, c3 and c4. In principle, I would only need to know 4 data pairs for those 4 unknowns. To estimate 4 unknowns, I need 4 data values, data pairs, yeah? To estimate n unknowns, I need n bits of pieces of information, okay? So, I have more data here. I already told you this, but that's okay. It doesn't hurt in most cases that you're going to work with. So, now the question is, how do we solve this problem? This is not an F0 problem of finding a root. In some sense it is. You can try solving it that way. You can solve this with F0 if you like to. Okay? But that's yeah, you can practice that at home if you want to. If you want to solve everything with F0, but we do it differently, okay? Here, this falls into the category linear system of equations. Okay? So we have all these data pairs, we have our equations, so now what we do, we set up the A matrix. A times C is B, or A times X, but X is confusing because we have X here. This is a different X as the X the author is talking about with A times X is B. So let's call that C. A times C is B. Now we set up A. Yeah, and A is this. The first row of A is simply x1 to the power 3, that's this one, yeah? The one on line 98, so the first one is this one, x to the power 3, then x squared, x, and this should be a 1. So that's what we see here, x1, x1 squared, x1, 1, times a vertical vector is, if we have, this is horizontal, times vertical, gives us an inner product, gives us a single number, and that's equal to the first measured value, y1. Okay, and that becomes B in our equation. Now the second row of A is the second data point, x. Now the same thing, we multiply that here with our vertical vector, gives an inner product, and it's equal to y2. Now that's how you set up A, yeah? So you have 6 times here an inner product, essentially, between 2 vectors, yeah? Now what I define here is, these are the x values, so they're taken from the table, yeah, our x values. Now here I define the matrix A. You should know how to do that by now. This is how A looks. Now, these are our B values. So these were our measured Y values. Yeah, you see them here. These are the measured Y values. Those are the B values. So the B values are always the measured Y values. Okay? You can't go wrong there. So what we have now is, these are the measured Y values. So we have A and we have B. And now we know that with A backslash B, we should have the coefficients. Now, these are our coefficients. Yeah, so we do Gaussian elimination, we use the backslash operator, which is identical to multiply on the left-hand side of B, B with the inverse of A. That's what it means. So again, multiply on the left-hand side of B, B with the inverse of A. So essentially this is equal to C is inverse A times B. But the inverse, can we use the inverse here? What is the size of A? Can we use the inverse here? No, because A is not square. So in other words, you need an alternative solution, which is Gaussian elimination, and this always works. Again, you need to set up the problem correctly, but this always works irrespective of the size of A. But you need to set it up correctly. So these are our coefficients. Yeah? So now we found our coefficients, so now we can obviously we can plot everything. So this is our data, and this is our model fit. You see? So this is our x data versus y data, and what I also included now is the straight line, is the fit between through the data points. So this suggests that our model is like piecewise linear, but in reality it's not. Like, so in other words, it looks like it goes like this, our model, but our model is much smoother, but I only plotted it at these values. Is that understandable? So it appears that this is a piecewise linear function, but it's not, it's a polynomial. So it looks much nicer going really smoothly through all the data points. But because I only plot their function at 0, 2, 4, 6, 8, and 10, it appears that this is piecewise linear. If I would plot it at many more points, then it would look different. Okay? So, now legend, we can add a nice legend here. So now you have the data and the model. Okay, so, now, is this a consistent solution? Remember, consistent, inconsistent. Consistent solution is that your model goes perfectly through the data. Now it appears, if you look at this figure, it appears that this is very consistent. It looks like the model goes perfectly through all the data points. So inconsistent would mean that that's not the case, that there is a residual left. Now how do we figure out again if a system was consistent or not? We can always calculate the residuals, but the other thing we can do is just rank A and B jointly, and you compare that against the rank of A, and they should be identical. If they are identical, then it's consistent. And why? A and B have the same rank as A alone. And why? What does this mean? That B is linearly dependent on A. Because otherwise A and B jointly would be rank 5. In this case. So you have to be a little careful with that sometimes. But because it also depends on the matrices. But we will not confuse you here. The size of A. Because you take the minimum of the rows and the columns. So you have to be a little careful with the rank. But in this case, A is of sufficient size. A and B jointly is 6 and 5, yeah, of size. And then you see that the rank is 4 and it stays 4 if you rank A alone. So in this case we know it's consistent. And why? Again, we mentioned this a number of times before. B is linearly dependent on A, which means that based on the information I have in A, I can, with some simple multiplication, scalar multiplication or subtraction or adding, I can go back from the information in A, I can perfectly derive B. Yeah, that's what linear dependence means. From 2 vectors in A or 3 vectors in A, I can derive B. Now that's great. That means that you can find a solution that perfectly predicts B on the information in A. B, and on the, you can perfectly predict B on the information A. Sometimes you hear my Dutch in between. I don't know if you noticed that. There's only a Dutch word in between. So I'm trying to teach you Dutch, but it's a little different language. I think it's interesting, like you have Germans, yeah, that's unfortunate, but you have those in this world. And so you have some people watch soccer here probably, or not? Yeah, the Champions League? Yeah. 2 German teams against each other, yeah? So the Netherlands has been in a World Cup final 3 times, yeah? In '74, that was Johan Cruyff. So we scored in the first minute. This was in Germany, okay? In Munich. So Johan Cruyff is one of the best soccer players ever. So if you look at the list, he's probably after Messi, I think is now, Lionel Messi is now the best player ever. At least that's what the stars say, that he's the best player ever. And then after that you have Maradona and Pelé. And then you have Cruyff in that list. And then Beckenbauer is a German guy, but he was a defender, so that's no fun, yeah? So anyway, so yeah, so in '74 the Netherlands played the final against Germany in Munich. So you play the World Cup final in that country, yeah? And so the Netherlands had the kickoff, so they had the ball and all that. And then at one point, Johan Cruyff was a player. You don't see that nowadays anymore. You would give him the ball in his own 16, yeah? At his side of the field. And then he would just go all the way forward alone. And then he will make one final pass and they would score. So they would never get the ball. They always felt like it's a marble or so that's connected to his feet. Yeah, it's like Messi, but even better at that time. But it's also much slower at that time. So anyway, Johan Cruyff, after about 1 or 2 minutes, he walked back to his goalkeeper, said, "Come here, give me that ball." So he gave him the ball, yeah. So he started dribbling and all that up front, and then they kicked him down and they got a penalty shot. So in the 2nd minute, the Netherlands. So we were leading 1-0. Yeah, and we got all kind of chances one after the other. And then the Germans got 2 chances or so. They got a little more. But they won 2-1 against the Dutch people. So it is really terrible, okay? I was -2 at that time, so I don't know this. But I do know that my parents were really stressed out. Maybe that was the reason to Yeah, I don't know what happened that night. Anyway, okay. Then in 78, believe it or not, we went to Argentina, yeah? Because the World Cup final was in Argentina. So again, we made it to the finals. This was in the Videla regime. I don't know if you know anything about Argentina. Videla was like a dictator, and a lot of people disappeared in his dictatorship. They were put in a plane, they were flying above the ocean, and then one by one were thrown out of the airplane. This is really true. And I don't know if you did it, so our Dutch, so we have a new king in the Netherlands, yeah? His wife, so that's now a queen, yeah, she became queen. Her father was part of that regime. Okay, and that's why he was not welcome in the Netherlands during the abdication, okay? So that was a big issue. Anyway, it's a sad story. But in 78, World Cup final, Argentina, Netherlands in the final. And we were 1-1 in the regular time. Then in the last second of the regular time, we hit the pole. And everyone said, even if we would have scored that goal, we were in Argentina in a corrupt regime with Videla, then the referee would have decided we just let the game continue as long as is needed for the people from there to score another goal, yeah, against us. It was so corrupt. So anyway, lost another World Cup final. The last one you've probably seen, the Netherlands against Spain. We didn't play very well. We shoot with Robben, two big chances. So anyway, 3 we lost World Cup finals, yeah. It's really sad, but it's a small country. But anyway, we're talking about Germany somehow, yeah. That was a sad country, yeah. So we have some time left, so that's why. But make sure that you study all this well, yeah. So Germany has 2 teams in the final, which is good. Yeah, so watch that Champions League. But the German soccer has changed a lot over the years. Up to about 10 years ago, there's some changes made. Klinsmann, who lives in California, by the way, was a soccer coach as a former player with Rudy Vuller. I don't know if you don't know these names, but he became head coach, and he said we should play as the Dutch team. It should be attractive. People come to the stadium to see nice soccer, and we want to give those people a good time instead of the way Germany always played, as defense-based. It was no fun to watch the German team. They would always wait, like the Italians, they would always wait for them to make a mistake and then they score. Whereas the Netherlands, they're trying to just be aggressive all the time. Yeah, it looks nice, but you can make a mistake. But when you win, it looks really nice. Anyway, so they changed in Germany. So now if you watch this final, it's much bit different. So that's a good thing. And why is that? Because 10 years ago, they actually started mimicking the Dutch educational system with soccer. Because we don't have money, we have to educate, yeah? It's true, because we're not the New York Yankees or so, yeah? The Yankees, they have so much money that they can just get any player they like, yeah? So whereas if you don't have money, like Real Madrid or Barcelona, they're really rich, they have a lot of money. So if they want a good player, they just pay, they have money. And they don't have it actually, they're bankrupt. But I have some rich people that will always donate money. Say, how much do you need at the end of the year? 100 million, here it is. That's how Manchester City works. We cannot do that in the Netherlands. So we have to educate these players. So the sad thing is, once our players become really good, then you have one of those oil people in the Middle East that give a phone call, say, yeah, how much is he? 75 million only? That's cheap. Oops, here it is in the mail. Gone. Player gone. And you start all over again. So that's why and so they are changing this in Europe now, that only financially healthy teams can participate in the Champions League, in the Euro League, which is a good thing, I think. Like England, look at England. Most of the players there are not from England, and that's what you see when they participate in the World Cup. They don't get anywhere anymore. No, it's true. Okay, so let's look now. We talked about the linear system of equation, so let's talk about the nonlinear system of equation, okay? Yeah? Is that okay when we continue? I understand the excitement of soccer, yeah? It's much better than the NBA finals. Oh. Oh. I was really happy. There was this... oh no, we can't go this subject, okay? Sorry. We can't talk about it here. That's a no and none. No. I'll be behaved. Okay. So one question though, before we continue, like, is a professor supposed to be in sorority house? Because I got like an email or so that they're going to celebrate like academic achievements, and I'm supposed to like the 3 kappa beta phi house or so. What is it? Tri epsilon gamma beta phi house, or it's some really mathematical house. I'm supposed to show up on Monday. I got this invitation. I'm like, should I go? Because I'm a little scared, yeah. So anyway. My girlfriend said, Jasper, that's the time of your life. I said, yeah, I know, better behave, yeah? I don't know the rules. Anyway, I'm a little scared, but Well, I've been there before. I mean, in that situation of being scared, not in that house. Okay, good. So let's start with the nonlinear system of equations. This is important, okay? We have 15 more minutes. So what we know, how to use F0, how to use the residual, how to plot functions that you look at it yourself. All these things are important for the exam next week. So let's look now at line 165 on the 166. We revisit the nonlinear problem of last Wednesday. This is also important because we'll go over 3 different solutions. It might be confusing what the author is doing in the book, so we'll try to do it a little better. So what we see here is we now have 2 equations, and we have one equation where only x appears, and we have one equation with an x squared. So remember, the previous example, we only had one equation that said y is c1 times x to the power 3 plus c2 times x squared plus c3 times x plus c4. Only one equation. We can set up the A matrix, but in this case, we suddenly have 2 equations. So what do we do now? Now, we can do the same thing as we did last time, and that's why the author says we do this with A times x is b, or A times c is b, which is better because we have an x in here, so it should be A times c is b, but it's very confusing, okay? So let's look at this. So there's 3 possible solutions to solve this problem. So essentially what we're trying to find that value of x for which both equations, both y values are identical. Now, how would you solve this yourself? We know from high school, we wouldn't do A times x is b, we would do this differently. So we can do analytical calculation, very easy. Yeah? We just set the left-hand side, 1.4 times x minus 0.6 is equal to x squared minus 1.6 times x minus 4.6. So you set the left side equal to the right side. Yeah? So both sides of y are identical. Now, the third approach is the residual approach. So the first approach is that we do A times C is B. We will do that at the end. We first do the analytical calculation, and then another approach is use the residual approach as we just talked about, okay? Now let's look at this equation here. We're trying to find those values for x and y for which both equations are identical. So essentially we're only trying to find a single value x, and for that value of x, both values of y in both equations are identical. So this is where it gets a little confusing what the author did in the book, because we can solve this problem much easier. We do not really need that Gaussian elimination. So in high school we have learned that we can solve this problem if we set both sides of the equation equal to each other. So we have 1.4 times x minus 0.6 is x squared minus 1.6 minus 4.6. So this is identical. If you reshuffle a little bit, that's equal to minus x squared plus 3 times x plus 4 is 0. Now, how have we know how to solve this problem in this case. I believe this was in the Netherlands, we call this the ABC formula. I don't know how that's called here. Is it still the same name, or did they change it over the last 10, 15 years? It's something like minus b plus a 1 minus the b squared. Yeah, do you guys know that? Yeah, you know that solution, yeah? Yeah, minus b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a or so, yeah? Now anyway, if you fill that in, if you want to prove, we can prove it. You just have to multiply both sides of this equation with 4 times a. You just write it out first in general form. So multiply both sides with 4 times a, and then you can nicely solve that. You derive very easy. In a few steps you can do it. But anyway, if you do this, then the solutions that you have for x are 1, minus 1, and 4. So in other words, if x is minus 1 or x is 4, both y values are equal to each other. So we don't need any Gaussian elimination. We just can solve this analytically. Okay? This is a special case because there is we can fill in this ABC formula. But if there would be a third power here, if this would be x to the power 3, we cannot do this. Okay? Now, so in the case that we cannot analytically solve this, we can just specify this thing as an inline function. So whatever we have left here, by setting both y values equal to each other and then solving for x, we're just essentially trying to find that value of x for which this is 0. Now, that's we know how to do this. This is the f0. And what we see here, that one root is minus 1, and that's with the starting value of 0. And then I can get another root. If I start at 10, I have a solution of 4. So I have two x values for which both equations have identical y values. That's x is minus 1 and x is 4. Okay? So if we fill out minus 1 in our equation, then you know what you're going to get here. If we fill out minus 1 here. Minus 1 times 1.4 is minus 1.4. Minus 0.6 is minus 2. So now one of our solutions is minus 1, y is minus 2, and the other solution is x is 4, y is 5. Now interestingly, the book comes up with Gaussian elimination, so we don't really need this. So in this case, please look at F0, because essentially what we did there, we wrote it down as a residual, and we just solved for the root. And we don't need Gaussian elimination, we don't need an iterative solve in the sense of iterative with Gaussian elimination. We can just solve this the way you already knew. And that is using F0. That's the same as the previous example, example 2. Very important this, okay? Now, but, okay, let's go back to method 1. So we talked about method 2 is analytical, method 3 is analytical, but then followed by using F0, because the analytical solution we cannot solve analytically, so we do that numerically with F0. The original method, as the author said, is we use a Gaussian elimination, is A times C is B. But how do we implement this in this case? Now, let's look back at these two equations. And it is that these are the two equations. Y is 1.4 times x minus 0.6. And the second one is y is x squared minus 1.6 times x minus 4.6. Now, how do we set this up in a Gaussian elimination style? Is that we bring the y into the equation. Okay? Now, so what we have is 1.4, but because that's a variable, we need to declare that as a variable that we do not know. And this is the part that's confusing. Because to solve this analytically or with F0, you only need to solve for x. Whereas with Gaussian elimination, you're going to solve for x and y. Because in the case that you do it analytically, you only need to solve for x, because as soon as you know x, you know y. So why do we need to solve both for x and y? It's a little strange. That's a little confusing. But that's how it needs to be done. So x and y are treated as unknown coefficients. And that's what we do here. So first thing we do is we will bring y into the equation and move this constant to the right hand side. Okay, so the same we do here. Now we can set up, what we can do, the trick is now, is to replace x and y with coefficient 1 and coefficient 2. So what we do here is we have 1.4 times x becomes 1.4 times c1 minus y is now c2 is equal to 0.6. And that this becomes c1 squared minus 1.6 times c1 minus c2 is 4.6. Now, we can now set up the left-hand side as matrix A, where we have 1.4 minus 1 is to accommodate c2, and then this is c1 minus 1.6 minus 1, again to accommodate c2. Now, that is equal to, times c1, c2 is equal to 0.6 and 4.6. Those are the values over here, 0.6, 4.6. Okay, so this is what we have essentially. Now, what do you see here? And that's why this is not preferred, is that we have an A matrix, and in our A matrix, our coefficient appears. And that's not what we like. We want our coefficients all to be in this vector, and that all this is known, so that we can estimate this unknown based on everything that's known here. But in this case, we have an A matrix with a coefficient in there. That's not desirable. So what we need to do is a numerical solution. And that is that we start at some value of C. So we define the starting values of C1 and C2. Based on that value of C1, we calculate the matrix A. Then we have A and B, so we can compute C is A backslash B. So we started with C0, starting, we calculate the A matrix, we calculate the new C values, we calculate the new A matrix, we calculate the new C values, and that's how you keep going. And at one point you will see that the C values are no longer changing. So that's how that successive substitution works. So if we fill this out, this is the number of iterations we do. So the number of times that we do this, we start with C, we update A, we calculate C, we update A, etc. The number of times we do that is 10 times. And our starting values for C are 0 and 0. Now this is what you see. What happens if we start at 0, 0, then the first case, updated case, for 0, 0, we calculate A. Based on A, we do C is A backslash B. And then our new value C is x1 and x2 is minus 1.33 and minus 2.4667. And you see, that this residual and then the L2 norm of that residual is important. That should go to 0. Is not 0, it's pretty large, 4.64. So that means this is not a good solution. Now, that's how you start iterating. At one point you see, hey, we're getting the same solution as we already had if we do this just analytically. Or we use F0. But there, we only need to estimate this one. Because if we know this one, we know that y is 1.6 over 1.4 times x minus 0.6. So if x is minus 1, then we know that y should be minus 2. That's 1.4 times minus 1 is minus 1.4 minus 0.6. That's our first equation of the two. So it's much easier to only estimate one and then derive this from the equations that we have than to consider them jointly. Interestingly is also, remember we had another solution. There's a second solution, that was x is 4 and y is 5. So this problem has two solutions. And unfortunately, that successive substitution is not telling us this. Yeah? And then you could say, you know, the starting values, try different starting values. Now, you know what? We'll try 4, oh, here we go, insert 4 and 5. And you see, once we use 4 and 5, look how great it is. It's perfect, because we supplied the answer. But what if we do 9 and 5? You see, it's going back to our original solution. So, look, we have 9 and 5 is one of the two answers. 9 is just wrong. That should be 4. But even when we start there, we go back to it. So what you'll see, you use a lot of different starting values here, and you always find only one solution. So, be careful with that successive substitution, so this iterative solver. So I suggest that if you have two equations, nonlinear equations, and you want to find the coefficients or those values of x for which their y values are equal, just use the residual approach. Yeah? And set that to 0. And use F0. So follow example 2. So example 2, example 3, and this last thing are really important, okay? And please read carefully all the things that I wrote there, because I explain everything is written out there. What I say here quickly now, so everything is written out in the text, okay? So again, next week we have 3 more minutes, okay? You are expected, please study this script really well. And please do not tell us that it's really difficult in the end, because the questions we ask are very similar to what is discussed in here. Or maybe the question or the actual equation and the data are a little different. It's a different problem, but the same concepts, the same things we're going to ask. Okay? Counts for 20%. Are there any questions, any comments? You will see the score. You already know your score. But I will send out an Excel worksheet tonight so that you all can see the scores. And you look at the tab, the sheets on the bottom, yeah? For your results. Okay, have a nice weekend.